Hi, welcome to another installment of Lo-Fi Effects Prototyping to Chill/Relax to. In the last video, I did a fair amount of branch management and refactoring. Today, I want to, in a sense, continue that work in the form of some corrections. Namely, it is about the assumptions that led me to write this comment here. To do. Decide whether this should operate at a fixed internal sampling rate. This is because the aliasing created changes a lot when the ratio between host and effect sample rate divide to an irrational number. So the host sample rate is 48 kilohertz, and you've instantiated this downsampler at its default of 44.1 kilohertz, for example. Changing the host sample rate then may change the sound of the effect, which we don't really want. But first, I want to address yet another thing. And this isn't quite this isn't a correction, but this is some extra context. Or in the previous installment, I said that I didn't like how you had to declare file dependencies in Cmajor patches. And I used this as an example. The issue for me was that you see that, so this is the main file here, and these are all of the dependencies, all the files with code that is used by that patch. Cool. The issue was this dependency here, oscillators, actually isn't directly used by the main patch. So at the end of the last installment, I wrote a message that I was going to post on the Audio Programmer Cmajor channel. And one of the Cmajor maintainers responded, and they said this: our expectation is that we'll have some sort of module package system. So you would bundle your dependencies into a module and include this in your patch. Basically, they haven't really gotten around to implementing this part of the language yet, which makes perfect sense. It's still early days and there's a lot of ground to cover, but I'm glad that is the case, that this isn't the final state of the language in terms of how you're expected to declare your dependencies. And actually, they also mentioned that they're writing some library type code as well that is making them think about this. So maybe it'll happen sooner rather than later. I hope so, because it would be a little bit nicer. But back to this comment. So there's an issue with this comment. The issue is the aliasing created changes a lot when the ratio between host and effect sample rate divide to an irrational number. Changing the host sample rate then may change the sound of the effect. Now, these things I've observed to be true. Here's an example. The first bit here is a electric piano sample with no effects applied to it. And this here, these are that same loop through the blit downsampling effect at different sample rates, at different host sample rates, but the same effect sample rate. So all of these are downsampled by the effect to 44.1 kilohertz. And then I've recorded the effect, processing that at 44.1, 48, 88.2, and 96 kilohertz. So here's the effect at a host sample rate at 44.1 kilohertz. And now, here's that same effect at a host sample rate of 48 kilohertz. Now, mind you, the settings of the effect are exactly the same. Okay. Now, here is the same effect, same setting, 88.2 kilohertz host sample rate. And finally, same effect, same setting, but at 96. So, given this, I made an observation that I thought was very intelligent. 44.1 and 88.2 work completely fine. Or at least they sound the same, right? 48 and 96 do not. Actually, no, you know what? No, 44.1 and 88.2 sound as expected, right? Because 44.1, if the effect is set to that and the host sample rate is also at 44.1, you shouldn't really hear any downsampling. And you don't really. What you're hearing, if a little bit of high end, roll off right here. There's that. You hear a little bit of crunchiness, probably from the nonlinearity of the. I think it's the output filter that has the distortion in it. So I thought, oh, it's because the host sample rate and the destination sample rate don't evenly divide, and therefore problems. I don't know. The issue is, I asked for help again. Thank you again to Stilson Smith, who has been patiently answering a lot of questions about correctly implementing this algorithm. Anyway, and he kind of was like, no, that's not exactly how it should be. And I wanted to, knowing that, hearing that feedback from him made me think, you know what, maybe I should do this same experiment with a different plugin. So this audio is from the TAL DAC set to, I think, linear. Yeah. The setting doesn't matter as much, right? As seeing whether it changes according to host sample rate. So that's at 44.1. And similarly to my downsampler, it's also set to 44.1. So here's the next one is 48, host sample rate, 48K. Sounds the same. .2 host sample rate. So we've established that this is not a thing that happens with other downsamplers. And of course, that doesn't necessarily preclude this part, right? Because assuming, right, if I were correct about that the aliasing changing that I was hearing is due to some innate challenge or some innate property of downsampling or the algorithm, we could say, oh, well, maybe they are also doing something like this where they're always operating at some high sample rate at the same sample rate. So no matter what, no matter what the host sample rate is, it will perform the same. But the thing is, I brought this up to the person who has been giving me all this information about how to do the blit downsampler, and they're not buying it. They're like, that doesn't make any sense, basically. Not in so many words. I think they were being nice. It was suggested that I concentrate on the oscillator. Well, there's not much to this algorithm aside from the oscillator, right? Because it's, you make the oscillator and you multiply the input by the output of the oscillator and put it through a spectrum analyzer, see if it's aliasing. Thankfully, at least in our case, it's not really that hard to see aliasing in a spectrum analyzer. We just have to know what harmonics we expect to see. What do you mean? Well, okay. So here you've got pigments. It's playing a sine wave, and it's playing an A. I turn this down. You hear that beautiful sine tone. Right? It's playing an A. And an A, it's playing a 2. Let's be specific. A2, yeah, right. Which corresponds to a frequency of 220 hertz. So a sine wave, we don't expect to see any harmonics. So we see one big spike at, basically 220. That it says 234 there, but I think this is more of a result of being all the way over here and having the cursor read weird. Yeah. So the important part here is that we have the one harmonic. We've got some stuff going on here. Not sure what this is, but as you can see, it is basically inaudible, right? Cool. So in the case of a sine wave, right, if we saw any prominent harmonics besides the fundamental, this 220 hertz, that's a pretty clear case of aliasing. Now let's spice it up a little bit, right? Let's do something that's got some okay, right? And I'm not going to do that too much because that can be really annoying. Yeah. Okay, so here we have a sawtooth wave, right? And here, basically what we expect is harmonics at frequencies that are integer multiples of the fundamental, right? So fundamental times x, where x is an integer starting at 1. So we expect to see a harmonic at, again, 220. I think more limit of the display than actual inaccuracy. Then we expect to find one at 440. Cool. Yeah, pretty much. And then we expect to find one at 660. Yep. And then, of course, we expect to find one at 880. And actually, I have this, if you'll notice, typically, right, a spectrum analyzer. Typically, a spectrum analyzer it's more useful for us in a musical context if it's logarithmic, using a logarithmic scale. However, I have it linear here specifically to point out that, to make it very obvious that these harmonics are spaced linearly. You can see that you have something that I guess looks like it could be some aliasing here. That's the thing. I'm not actually sure. I'm not totally straight on, when you would, it probably is aliasing, right? Because it's just a pure saw wave. We don't really expect to see anything. In an ideal world, right? All we see is the harmonics at even multiples of the integer, but there's also, there's other, oh yeah, see, there's a filter in here. Oh, it gets worse. Interesting. Okay, yeah, see, so we've definitely got a little bit of aliasing, which again is pretty quiet, and it's very hard to, I wonder if you can turn on, if there's like oversampling you can turn on. Multi-core? No, sorry, I'm getting distracted. Either way, so you get the point. And one thing that I think is important to say about this is it's not really a measure of quality per se. You should really use your ears. But it definitely is a tool for understanding what is going on when something very clearly, or when something seems to be wrong, right? Like how much aliasing is okay. Most of the literature, none of the literature claims to eliminate it, right? What it does offer is, hey, we really decreased aliasing for these nonlinear effects or for these oscillators. So we've gotten aliasing down to a level that it doesn't really sound significant, or there's some kind of balance between the CPU resources required for creating the effect and the sonic result. But anyway, so that's the basic, very, very basic primer on aliasing, or at least on observing aliasing. In order to investigate this, I implemented a new Cmajor patch called Blit Troubleshooting. And it's pretty simple. It's just the Blit oscillator that is used by the downsampler and an output gain for safety. It's going to run at 220 Hertz, like in the previous example with pigments. We expect harmonics at 220, 440, 660, 880, 1100, and 1320 Hertz. So, like, you know what? So, let's ditch this. It'd be easier to, we can look at this. Yeah, 220, cool. 440, cool. 660, okay. 880, 1100. That actually seemed fine-ish, right? But check out what happens when we change it to 3500 Hertz. And also, when I'm gonna move from the linear to the log, just because it feels easier to grab hold of these, especially when the fundamental is kind of low. I guess the fundamental is not low here, but I've switched to log. So, okay, first of all, we've got a harmonic of 700 Hertz. Now, 700 Hertz is, well, 3500 is divisible by 700, right? The issue is that we shouldn't have harmonics underneath the fundamental. That is very, 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 very obviously aliasing. This is something that Stilson Smith told me to look out for. Basically, harmonics basically either not being like frequency peaks at places that aren't even harmonics, or generally just harmonics not showing up where they should be, where they should be, right? So again, here is, so I'm going to call this 1.5. No, it's not 1.5. It's 1.4 kilohertz. Either way, shouldn't be there because it's underneath the fundamental. Shouldn't be there underneath the fundamental. Shouldn't be there underneath the fundamental. Finally, here's our fundamental. And so the next harmonic, right, should be 7 kilohertz. But we have one at 4 0.22. You know, let's see, is this the one? Yes. Okay, so here you can see, so that this is this is a legitimate harmonic. This is a legitimate harmonic. I'm going to guess that this is also a legitimate harmonic. Let's see, 7.7. So it'd be just 10.5. Yep. Okay. So this is aliasing really badly for certain ratios between host sample rate, right? Because I haven't changed the host sample rate here, but I have changed the destination sample rate. So for certain ratios of sample rate to effective sample rate to host sample rate, it seems to work fine. But for other ones, it is full of aliasing. So the question is, how do we deal with that? Well, one thing that we have is, this is a throwback to maybe the second installment of this series where I was still trying to figure out how to implement the band limited impulse train. And I found an implementation from the Synthesis Toolkit. I listened to their implementation and my implementation, and I preferred the way mine sounded. Now, here is the thing about that. I've brought back the Synthesis Toolkit version of the band limited impulse train. What we can do here is simply change the calculation we're using. Let's see what happens. So when I save this, we should be seeing, holy smokes, look at that. We've got 3.5, 7, 10.5. And then if we switch back to linear, yeah, I mean, they look evenly spaced. So, even though I didn't like how the Synthesis Toolkit version sounded, they're clearly doing something right where I'm not. Which brings us to the next question. How do I fix this? Part of me is tempted to simply say, okay, cool, we'll use the Synthesis Toolkit version. However, since I am a punisher, since I am an enjoyer of self-improvement, I want to do my level best to understand what I did wrong in terms of the calculation. So in order to figure out what I've done wrong, I'd like to start by making the problem as small as possible. There could be a lot of surface area, right, if we don't think about it correctly. So what I mean by that is, clearly all of this works, right? And this works, all of this works. We know this because, actually, well, I'm not sure about this. I missed this. All of our problems go away when we change from this calculation to this calculation. Okay, so what does this calculation use? This uses phase, which is wait, what? Okay, so I've done something not very nice here. So as you can see, I write this in such a way that it takes an argument that I don't even use, which is confusing. So let's do something a little bit different. Do a little refactoring. And let's hope that that all builds. Oops. Okay, cool. We're still good. Looks good. Awesome. Right, because the phase is a member variable. It's getting iterated upon outside of here, which we might want to think about refactoring that to make it more clear, but whatever. Factoring it this way allows us to really easily change the algorithm without rewriting this in both places. So what we do know is that we are correctly calculating phase. Cool. We are correctly calculating M, which is, what is M? That's M. Okay, cool. That's good to know. That also means, right, M is correct. And I say M is correct, right, because tick SDK depends on M. So if this was being calculated incorrectly, so would tick STK. Cool. And P. So I'm going to put these notes up here. That's correct. Is there anything else that we can determine? Oh, okay, cool. So rate is correct. I know that rate is correct because the change of the phase variable is correct. And in order to do that, we need to have the phase. Oh, sorry, the rate. We haven't verified this. This is only used here, and it is meant to be a little tiny optimization. But I think what we need to do is simply this is not a lot of code. I think it would be better to redo this and do it in the most naive way possible, right? So let's take a look at, nice. Let's take a look at the paper again. Okay. Where are we? Okay, so band limited impulse train synthesis. So y of n equals m divided by p times sync. And the argument to the sync is m/p times n. Okay. Where sync equals so the first thing that we should do is let's separate out the sync function. Float sync. Return sine times. Oh, we actually do need x, or I guess coefficient type x. Actually, I'm going to see if I just can get away with float. Right, return sine of x, no, let's see, pi times x. Oh yes, and this is where we need to basically split it up because we need to test the denominator. So let denominator equals m times sine pi times x divided by m. And I will cast these to, oops, have to cast pi to coefficient type. Right, so m times the sine of pi x over m. M times sine of pi times x over m. Let's borrow this. If our denominator is too small, we're going to return 1. And then we are going to return sine times pi x divided by denominator. Okay, cool. And you know what? Let's tick troubleshooting. Why not? Okay. Let's take a look at this. M divided by P times sync and I'm going to be silly, right? Return M divided by P. Might yell at me about casting. Might yell at me about a lot of stuff. Times think M divided by P times phase. Okay. There is one other thing we need to do. Now, if you'll notice, this works by going up to adding to the phase until it goes up to pi and then wrapping it. That is a simplification or an optimization that allows us, like the SDK implementation is written like that, it allows us to not multiply by pi every time, because as you can see, every time there is a multiplication with the we're actually going to and tick troubleshooting. Let's see if that even works. It might yell at me about something. Oh yeah. Cannot find simple P. Doesn't know what P is. Okay. Why does it not know what P is? Oh, okay. This is because the way I was calculating this didn't require us to store P. Coefficient type, oh yeah, P. Oops. That looks even worse. Still not looking great. still not good. Yeah, see, okay, here's another way of seeing that like your stuff is not good. Like I'm cranking the frequency up. These harmonics should only be going up. They shouldn't be like dancing around. That's real. That is a what I like to call a warning sign. Okay, here we go. Yeah, no. This is also not working. As you can see, this is worse than I had it before. No, that doesn't really do anything either. Okay, well, I'm just gonna delete that failed experiment. Let's revert a bunch of stuff. Actually, I think we can revert everything. Go back to the tick STK, which works. I'm going to have to punt, I think. We have an algorithm that works. And at the end of the day, that's going to have to be good enough. I'll probably do a little bit of reading off screen in order to figure out, or at least to try to come to a real understanding of how to correctly execute this algorithm, implement this algorithm, because the fact that I had to pretty much just copy paste it from here, I mean, that's kind of what it's for. This is MIT licensed code, right? So that's kind of the point. And you could argue, well, why reinvent the wheel? Well, I'm not a DSP engineer. This is a hobby, and the hobby is meant to, expand my abilities and try to understand things a little bit more than I did before. So, kind of frustrating. Oh well, I'll probably ask somebody for help. So yeah, that's going to be it for now. Thank you as usual for joining me.